more efficient by storing fuel within the structure instead of needing parasitic tanks. Speed in this time period now is, the breaking the sound barrier was achieved by Chuck Yeager, and now we're, by the end of the 50s, up to 1,500 miles per hour. Okay, in the 60s, titanium continued to increase, but now composites are starting to come into play. Composite, particularly carbon fiber, offer the potential to be 5 times the strength of steel. And so this is really the birth of composite applications. Honeycomb sandwich came into play. So that's essentially afforded lightweight structure. Honeycomb, as it sounds, it looks like a honeycomb. Essentially, it's sheets of metal or paper bonded together at nodes that are then expanded and form a cellular sheet that gives you a very strong but lightweight structure. This is the first use of carbon, high-flow carbon in an engine application. And now the speeds are in excess of 2,000 miles an hour. Okay, what are the helicopters doing in this time period? Well, in the 60s, we were still pretty much all metal construction now of the blade. So we've gone from wood to metal. Similar design. A spar was extruded aluminum. The ribs were aluminum sheet metal. And then the skins were essentially aluminum sheets that were fastened with rivets to the other metal components. We did use some nickel on the leading edge to prevent erosion. As I mentioned earlier, sand and rain really can degrade a rotor blade very quickly. Now moving to the 70s. Now you'll notice, let me just go back. So here we're at 2,000 miles per hour at the end of the 70s. As we get into the 80s, we're now at just over 2,000 miles per hour. The Concorde flew at Mach 2.2. Materials were, for the Concorde, the supersonic Concorde, were primarily aluminum, but the aluminum actually wouldn't have been able to achieve the operating conditions that the Concorde was designed to fly to, because the thermal heating from going that fast was degrading the aluminum. So they actually developed a reflective white paint that reduced the temperature by 20 degrees that allowed them to continue to use aluminum and keep the costs within the parameters and the design within the parameters that they had intended. Again, composites are now rapidly being applied, particularly in the military application. Okay, now, Sikorsky's blade design in the 70s has now transitioned from aluminum to titanium. We had a titanium spar now. We had more advanced airfoil shapes. It's fairly costly, but now we're also starting to introduce composites. So instead of aluminum skins, we went to fiberglass skins. We used honeycomb cores that were bonded to this titanium spar. We had lead epoxy counterweights to better control the mass balance of those parts, and nickel abrasion strips for erosion. In the 80s, now we're dealing with the space program, fully mature. We're now gone from 2,000 miles per hour to re-entry speeds approaching 18,000 miles an hour. Again, not possible without the introduction of several materials, primary of which were the space shuttle ceramic tiles, which had to function from 2,200 degrees Fahrenheit down to 40 to a 40F shock without incurring damage. That allowed that Mach 25 re-entry into the Earth's atmosphere. Thermoplastics, polyether ketone in particular, started to become introduced. Those are materials that you can form to shape versus cure to shape. Toughened epoxies started to improve composite properties to the point where they were now becoming structural instead of just secondary structure. Sikorsky developed the S-75, which was a purely developmental aircraft, but was an all-composite airframe program. So this was our first venture into composites. It resulted in a weight savings of 23%, cost savings of 20%. It employed a number of different composites, Kevlars, graphites, pultrusion, pre-preg technologies, sandwich construction, filament winding, graphite fabric. So a variety of composite technologies, purely a development program, but what it allowed was now this technology to transition to our production aircraft. So composites at Sikorsky in 1985, every component you see out there represents composites on our S-76 and Black Hawk and CH-53 aircraft. It's predominantly secondary structure, doors, fairings, some airframes, some airfoils. And this is just a cartoon of our S-76C Plus aircraft that shows you where the materials tend to be used. So 76C, aluminum, the blue, was still being used for airframe. Composites, again, secondary structure, graphite, honeycomb, the red, and Kevlar on the yellow structure. Blades were a hybrid of titanium and composite. Tail blades were all composite. 1990 to 2000, we started to get really aggressive with the use of composite structure. The Comanche was a scout attack aircraft developed for the Army. Never went to production, but it did lead to the development of over 60 new materials that we use on our several programs today. The carbon fiber and epoxy developed for Comanche is now used on the S-92. A lot of emphasis on damage tolerance, a lot of emphasis on durability, and obviously lightweight and speed. Carbon epoxy and fiberglass now is the norm for our rotor blades, so titanium's been eliminated, everything's composite. What that does is allow us to tailor the structure to achieve what we used to do with mechanical joints. So with a metal structure, you needed hinges and joints to take the motions of a rotor blade. Rotor blades flap, they have a lead lag motion depending on where they are in the rotation, and they have a pitch that drives the direction and the altitude of the aircraft. Well, to do that with metal, you needed joints to accommodate those motions. With composite, how you orient the fiber allows you to achieve those motions without a joint. So that's a huge advantage of composite design. On the S-92, again, similar to the S-76, this shows use of composite on the main rotor blades. Again, on the secondary structure. The airframe itself is still blue. Anybody want to venture to guess why we didn't go to composite on the airframe? Sort of. It was a business reason, but not necessarily expense. The S-92 was produced with partners all over the world. Our partner for making the airframe was in China. And we had export regulations that prohibited the export of composite technology to China. And to achieve the lowest cost airframe using China as a partner, this airframe stayed as metal. So again, thinking back to that pyramid of material selection, it's not always the best performance. Sometimes there's a business aspect that drives your decision on what to use. Okay, 2000 plus. Glare is a hybrid of aluminum and fiberglass used by some of the companies in the European theater, particularly Airbus. Boeing developed the all-composite 787. It's actually 50% composite by weight, 80% by volume. It's 25% more efficient than the 767. So again, trying to make your aircraft fly faster, be lighter, be more efficient for fuel is the constant driving force in aerospace. This is also the onset of what I'll call designer materials. The understanding of the constituent properties of materials, in the case of metals, right down to the grain level, the grain boundary level, allows companies like Questech to develop and invent materials based on that understanding at the nanoscale. We're trying to actively get rid of chromium from our paints, primers, adhesives, because of its carcinogenic nature. We're looking at alternate technologies for additive manufacturing, advanced fiber placement, nano reinforcement. We're trying, I talked about the structural building block approach, which is a very rigorous, time-consuming, expensive process to develop properties. By use of process modeling, we think we can reduce the amount of testing we need to perform if we can analytically predict the behavior of a material by understanding those micro properties and then translating that to components without actually having to do as many tests. Ceramic matrix composites for hot sections are coming into play because they're much lighter, about 40% lighter than some of the heavy superalloys, metal superalloys. And a term, integrated computational materials engineering, ICME. That's one of the material genome initiatives identified by the Obama administration, and it's essentially trying to take that constitutive understanding of a material through its entire life cycle, so you can, again, analytically and through models, predict lives, control material usage on aircraft, and ultimately its retirement. This just gives you a general sense on the percentage of composite usage over time. Again, as we progress to the right, from the early 70s at the inception, in a fairly short period of time, they're becoming the predominant choice for designs, not just within aerospace, but throughout industry. The automotive industry is moving towards it. So those of you who are mechanical designers, I urge you to become familiar with composite materials and the analytical approaches for composite design. Okay, glimpse of the future. Basically, we're going to go faster and faster, and autonomy, flying with or without a pilot. You see drones all over the news these days. Our aircraft we're trying to develop so you can use a pilot or not. That it's optional, that if that crew has to help attend to a passenger in the back, if you're an emergency medical mission, that crew member doesn't need to fly the aircraft. He can leave a seat and can attend to passengers as need be. It can reduce the workload of the pilots to the point where they're focusing on other aspects of their mission rather than the flying of the aircraft. Speed. Helicopters had kind of hit a threshold of around 180 miles an hour. With the X2 a couple years ago, we achieved 250 miles an hour. Technologies that we're looking at now potentially push it to 300, 400 miles an hour and still retain the function